There are three basic properties of gases. And when we talk about states of matter, we have solid, liquid, and gas, as you might have seen in some of our other videos. The basic property of a gas are three, which is volume, temperature, and pressure. You can describe gases using those three basic properties. But of all the three properties, the one we're going to focus on in this part of the video is pressure. All right. So pressure in itself is equal to the force divided by the area. Okay. So when we say force, from Newton's law of motion, the force is equal to the mass multiplied by your acceleration due to gravity. Okay. That divided by your area. All right. And we can go a step further when it comes to the description of pressure by saying that it's equal to density multiplied by volume multiplied by the acceleration due to gravity. That's when you want to describe the force divided by the area. Then we can also move a step ahead by breaking this down. When you say volume, volume in itself is equal to the area, your L cube here, times the height, times still multiplied by G divided by the area. Now we're getting somewhere. So when you cut area cancel area, what you will be left with is pressure equals, what do we have? Density times height times G. That's your or in some cases you might have something like this: P equals to density times height times G, and that's the formula for pressure. Yeah, formula. Okay, and we have to describe pressure in terms of units. Okay, so for the unit, we'll say that the unit of pressure is Newton per, did I write cube? Newton per meter squared. Okay, and 1.013 times 10 raised to the power of 5 Newton per meter squared is equivalent to 1 atm. That's 1 atmosphere, and that's also equivalent to 1.013 times 10 raised to the power of minus 5 pascals, and that's also equal to 760 mmHg. Okay, all this just describes the atmospheric pressure, the density of the gas multiplied by the height and the acceleration due to gravity. I'm sure you must be wondering, how do we know the height of a gas? How do we piece all those things together? Okay, and I'm going to show you right about now. Okay, so to measure the pressure of gases, we use an instrument that we call a manometer. Okay, it's spelled manometer. All right, so if you have to look at the diagram you have here, okay, if you have to describe the pressure of gases, okay, according to this diagram, we can say that the gas pressure, okay, at X at this point, okay, gas pressure at this point is equal to the pressure in the liquid. That's this particular liquid at what point? At point Z. Okay, so you guys can just follow the pointer at point Z. Okay, at that particular point. Okay, at Z. Okay, so the pressure at this point is equal to the pressure in the liquid at this point. That's what we're saying. Okay, so if you had to break that down, you would say that the gas pressure at X is also equal to the atmospheric pressure. All right. Okay, let me cross my T's. Atmospheric pressure plus the pressure due to the water column. Did I get that correctly? Yeah, column YZ. All right. Okay, so the pressure at X can be also said to be equal to the pressure at Z. We said that earlier, and the pressure at Z is also the pressure caused by this water column. That's what you have here as H. Okay, so the pressure caused by this height is also the same as what we mentioned earlier. So if you want to rewrite this, you can say that gas pressure, okay, equals to the atmospheric pressure, all right, plus h. So that's on one side. Okay, now on the other side, all right, you have this diagram right here. Okay, so you have this analogy right here. Okay, up here you have the atmospheric pressure. Here the liquid you have here is mercury. All right, liquid you have here is mercury, and up here you have your gas. Okay, so if we are to know and calculate the atmospheric pressure, okay, at this point n. Now remember our previous discussion concerning how manometer works. The pressure at n is also equal to the pressure at m. Okay, so at n, what you have there is not the gas pressure, is actually the atmospheric pressure. So we can say the ATM pressure at n is equal to the pressure of liquid. That's at m. That's at this point right here. All right. So if you want to break this down, you would say that the pressure of gas. Okay, so want to break this down now into two. So you say the pressure of gas plus the pressure, I'll just write P due to mercury coulomb Ln. I'll just take that again. The atmospheric pressure at n, you know, we said is equal to that at n, and it's equal. That means if you want to expand the equation you have there, you know, the pressure of gas at this point plus the pressure due to the mercury coulomb, that's Ln. Okay, so if you have to trace it here, you have L here, you have M here. Sorry, this line is not too straight. So that's kind of like the pressure of the liquid. So that would be the atmospheric pressure equals the pressure of the gas P at this point plus the height, that's the column Lm that you have here. This is L, this is M. So just that's the height you have here. So that's what we just turned into the height. And you know, if you have to rearrange this, we want to make P the subject of formula. So that's, we want to make the pressure of the gas the subject of formula. That will be the pressure of the gas equals to the atmospheric pressure at n, that's at this point, okay, plus, is that plus? No, that will be minus h. Okay, so remember that this guy is the pressure of the gas. I have a question here. It says if the specific gravity of mercury in the water manometer is 13.6 and the ATM, that's atmospheric pressure, is 70 centimeters of mercury, what is the total pressure of the gas supply in centimeters of water? Okay, now first things first, what I want you guys to know is when we use the word specific gravity is the same as saying relative density. Okay, now that on one side. On the other hand, we need to know what relative density is. Okay, now relative density, the formula for that, okay, I'm so relative, it means we're kind of like comparing the density of two things. Okay, for those of you who have no idea what that is, we are comparing the density of two substances. So the first substance we have, that's the density of substance, which in the case of this question we have here, that's mercury, okay, divided by the density of water. So the density of water is like the standard, so we compare the density of so many substances against that of water. Okay, fine. So let's now try and know what the value of this guy is, because that is very key to getting our answer. So the density of mercury, okay, now from this formula, if you were to make density of substance, that's of mercury, the subject of formula, now when we cross multiply, it will be relative density multiplied by this guy right here. So that will be, I'll just write relative density as RD. Okay, let me just have it as RD multiplied by density of water. All right, all right. Okay, so since we established the fact that specific gravity is the same thing as relative density, so we just plug in 13.6 as we have it from the question multiplied by the density of water is 1000 kilograms per meter cubed. So when you multiply this, you should have 13,600 kilograms per meter cubed. Now, remember that when we're talking about calculating density of substances in a manometer, we most times do a comparison and we resolve that. Let's say the pressure at this point is equal to the pressure at this point, that's the atmospheric pressure, plus this height of the liquid column. So that will serve as the basis of the next thing we're gonna do just right about now. So we can say that the pressure of water, okay, let's just say, all right, pressure of water is equal to pressure of mercury. There you go. Yes. Okay, so and you know, for pressure is your rho times height times gravity. Okay, remember that's for water equals to your rho times height times gravity. For mercury, that's Hg. Okay, okay. Now let's just expand this now. So the density of water is 1000 kilograms per meter cube. We said that earlier, multiplied by the height. Okay, that's what of the keys to our answers. The height of the water, because that is very key to getting our answer, multiplied by g, which is the acceleration due to gravity, and that would be equal to the density of mercury that we got here. That's 13,600 multiplied by 70. Now we'll have it from there. Next time, that the height of the mercury in the manometer is 17 centimeters. You know, that just depicts the atmospheric pressure in on that end. All right, so times 10, that's your acceleration due to gravity, and it also depends on the g you're getting from the question. In solving this, we'll refer to use 10. In some questions you might have that's 9.8, so just check the questions very well for you to know the value of g that you're giving. So that would affect this as well. G will be 10. So we have to make h the subject of formula. Okay, so right here, h will be equal to 13,600 multiplied by 70 times 10 over 100, 1,000 times 10. And if you should plug that into your calculator, you should have 952 centimeters. Okay, and remember the principle we're talking about when you're solving this kind of question, that's the pressure of the gas, okay, is equal to the pressure at this point plus the pressure due to the height of this water column. So what we get from our answer there is the pressure at this point. So we have to add the height of this water of that column. Okay, it's not of that column. Okay, so we're just gonna add 3 to that. So to buttress my point, that's the total pressure. What I just said some minutes ago is the atmospheric pressure plus pressure due to water column. Remember this formula. That's N. Okay, so that would be 952. We got that from the question, plus 3 centimeters. So that would be 955 centimeters of water. So there you go. That's our final answer right there.